In section 5.4, we're going to look at a new term called sampling distributions and then also the central limit theorem. The first definition we have is what a sampling distribution is. I'm not going to read that to you. You can read through this, but what I'm going to do, which I think will be more beneficial, is after you've read through the definition, then pay attention to how I explain that definition using this Venn diagram. What we're doing is when we create a sampling distribution, we are taking a population of whatever size, and we're pulling random samples from that population. So let's say we had 100 people in a classroom, and we were going to randomly select 5 people. So that would be the first random sample 1. And then I put all those people's name back in there, and if we're drawing from a hat or whatever, and I choose another random sample of 5 people. So it is possible that some of the people who were selected in one sample will be selected again in another sample because we're always putting them back into the mix. Okay, so what happens is we create all of these random samples. So this example is showing that there's 5 random samples. And what we're going to do is we're going to find the mean of each random sample. So that's what you're seeing here. The X bar 1 represents the mean of random sample 1. The X bar 2 represents the mean of the random sample 2. So if I find all of these means, what we end up with is the sampling distribution of sample means. We're getting a sampling distribution, and we're taking the sample means of that sampling distribution. So a couple of properties of sampling distributions of sample means is first, that the mean of the sample means will be equal to the population mean, and we'll show that here in example 1 in a second. And the standard deviation of the sample means will be equal to the population standard deviation divided by the square root of the sample size. And that standard deviation is called the standard error of the mean. Now, we're not going to use these right away because I'm going to show you in example 1 how to get the answers, and then we're going to show that these two properties hold. And then after that, if you will remember these two properties, or these are things I would consider writing down on the formula card, you have these written down, then you can use these shortcuts to find the answers to future questions. So the first one we're going to do is example 1. I'm going to first show you how to create a sampling distribution, and then how we find the sample means, and then how we find the mean, variance, and standard deviation of the sample means. So the first thing we're going to do is we're going to create a table. And it's actually, there's 16 entries in our table, so I'm going to just do 2 side by side to have room to put them all in. Okay, and what they tell us is that the number of times 4 people go to a grocery shopping in a month is given by the population values 1, 3, 5, and 7. So one of the people in our population goes once a month, one goes 3 times a month, one 5 times a month, and one 7 times a month. And that's what they're showing you here, that 1 out of 4 people goes to the grocery store once a month. And that's 1 out of 4 would be 0.25. 1 out of 4 people goes to the grocery store 3 times a month, which would also be 0.25. And that's what the histogram is showing you. What we're going to do is create samples of size n by randomly selecting 2 people out of the 4. And it says with replacement, which means after you choose the first person, you're going to put them back in the hat before you draw the second person. So we're going to create all the different combinations of 2 people chosen out of the group of 4. So I could choose the person that went once, put them back in the hat, and choose that person again. I could choose the person that went once, put them back in the hat, and draw the person that went 3 times. I could take draw the person that went once, put them back in the mix, draw the person that went 5 times, or 1 and 7. Or I could draw the person that went 3 times, and then draw the person out that went once. Or I could draw the person that went 3 times, put them back in the hat, draw 3 again. So all I'm doing is creating all the possible combinations of 2 numbers from this group. So 1, 1, 1, 3, 1, 5, 1, 7, 3, 1, 3, 3, 3, 5, 3, 7. So now I'm up to 5. So I could have 5, 1, 5, 3, 5, 5, 5, 7, or I could have 7, 1, 7, 3, 7, 5, or 7, 7. So those are all the possible combinations of 2 people chosen out of the 4. Okay, so this is the what I've created is the sampling distribution, and now they want me to find the sampling distribution of the sample means. So they want me to find the means of each of these samples. So we call the mean, remember, x bar. So when you're finding the mean, you're adding and dividing by 2 because there's 2 numbers in our sample. So I'm going to add 1 plus 1, do this up here, and divide by 2. I'm going to add 1 plus 3 and divide by 2. I'm going to add 1 plus 5 and divide by 2 and go down the list and do all of those. So this would be 2 divided by 2 is 1. This would be 4 divided by 2 is 2. This would be 6 divided by 2 is 3, and just keep going down the list and doing that. So I've now created the sampling distribution of sample means. Now they asked me to find the mean, the variance, and the standard deviation. If you'll recall, the mean, and this is the mean of the sample means. So to find the mean of these numbers, 1, 2, 3, 4, 2, 3, 4, 5, we're just going to add all of those numbers up and divide by, there's 16 entries here, divide by 16. So when I add all of these up, and I'm not going to write them all down, I'm just going to give you a start here. So I'm adding 1 plus 2 plus 3 plus 4 plus 2 all the way down until I get to the plus 7. And then there's 16 entries, so I'm going to divide by 16. These numbers all added up give me 64. Divide by 16 would be 4. So the mean of my sample means, so the mu for the mean and then x bar for the sample means, the mean of the sample means is 4. Okay, kind of going back a ways, back in chapter 2, we learned how to find the variance. And the variance of the sample means, so our symbol for variance of the sample means would look like this. And remember, variance is squared, and then when we do standard deviation, we take the square root, so we take the square off. Okay, if you'll recall, this is the sum of each entry minus the mean. So the sum of x minus 4, or 1 minus 4 squared, and then 2 minus 4 squared. So this goes, again, back to chapter 2. So if you've forgotten how to do variance, you can go back to chapter 2 and look over that again. But in general, our formula is we take each entry and subtract the mean, and then we divide by the number of entries. So in this case, it's going to be each entry is x bar, and then we're subtracting the mean. So to fit the what we have here, we're subtracting the mu x bar here. And that's what we're going to do, and we're going to square it, add all those up, and then divide by n. So I'm not going to go through every one of them. I'm just going to kind of go do this to refresh your memory. So to get the x bar minus mu x bar, you take the first number, 1, subtract the mean of the sample means, which was 4, and square that. And then we take the second number, 2, we subtract the mean, and square that. And we keep doing that until we've gone down the entire list. And that's how we get this, the sum of these differences. Okay, so when you do that, like I said, I'm not going to do all of that here. When you do that, you're going to end up with the sum of all of those ends up being 40. And then we're going to divide by 16 entries, and that ends up being 5 over 2, or 2.5. So that is my variance of the sample means. And then the last one is the standard deviation of the sample means. And that one's easy because we've already done all the work. That is simply going to be the square root of the previous answer, the square root of the 2.5 that we just found. So that's going to be, let me get rid of that. That's going to be the square root of that number that we just found, which was the square root of 2.5. And then that's going to come out to about or approximately 1.6 when you take the square root of 2.5. So it's approximately 1.6. So that is our standard deviation of the sample means. Okay, and I promised that I was going to show you a shortcut to get all of these if you knew information about the population. So if we go back up and we look at the rule up here, it says the mean of the sample means will always be equal to the population mean. So if we look at what they gave us the mean of the population was 4. And what did we find the mean of the sample means to be? 4. So if you know the mean of the population, you automatically know the mean of the sample means. They gave us that the variance was equal to 5. And according to our rule up here, the variance of the standard deviation of the sample means will be the population standard deviation divided by the square root of n. So if we come here to the standard deviation was square root of 5, that means the variance was 5, because you just go in reverse. So for our variance, it's going to be 5 divided by the square root of our population size. So we had 5 divided by 2, which is 2.5. And then once we do that, to get our standard deviation, we just take the square root of that number. So that will show you how you can do a shortcut. And you can, if you're given, now you can't do this if they're not given these values, but if you're given all of these values, you will be able to quickly find the values for the sampling of the sample means. So you'll be able to find the mean, variance, and standard deviation of the sample means using these properties up here. All right, so let's look at a couple more things. This is just giving you the probability distribution. So for example, here, the mean of 1 occurred 1 time. So the probability of that being the mean would be 1 out of 16. We had a mean of 2 occurring twice out of 16. We had a mean of 3 occurring 1, 2, 3 times out of 16. So that's what this is showing you, the probability distribution. And then this is showing you the probability histogram. So those are just kind of the tables and graphs that we've been doing throughout the semester. All right, so the second thing we're going to look at is called the central limit theorem. And the central limit theorem describes the relationship between the sampling distribution of sample means and the population. So we've kind of already looked at a couple of properties that tied those together. This is a theorem that actually tells you that this is what always happens, or this is always the relationship between the sample means and the population the samples are taken from. This is an important tool, provides information you'll need to use sample statistics to then make inferences. And we'll be doing that a lot in Chapter 6. We'll be making inferences about the whole population based on what we know about the sample. So here's the central limit theorem, and I'll walk through this slowly before we do an example. So on this one, it says, if random samples of size n, where n's greater than or equal to 30, so in other words, you're pulling samples of size 30 or bigger, if those are drawn from any population with a mean and a standard deviation given, then the sampling distribution of the sample means will approximate like a normal distribution. So if you remember that, the normal distribution means that you have the bell-shaped curve going on. The greater the sample size you pull, the better your approximation will be. On part 2, it says, if the random samples of size n are drawn from a population that's normally distributed, then the sampling distribution of sample means will be normally distributed for any sample of size n. So if you have a normally distributed population, then it doesn't matter what sample size you have, the sampling distribution will be normally distributed. In either case, this is true. We have the sampling distribution of sample means will equal the population mean, and we've already talked about that property above. The sampling distribution of the sample means has a variance of 1 over n times the variance of the population, and a standard deviation equal to the population standard deviation divided by the square root of n. So if you'll recall, we didn't have them written out exactly like this. We had the standard deviation. We didn't have the variance, but that's again what we have up here. So this is putting those pieces of information into a formula. Remember that the standard deviation of the sampling distribution of sample means is also called the standard error. So the problem may ask you to find the standard error. They mean you're finding the standard sampling distribution of sample means, standard deviation. The distribution of sample means has the same mean as the population. However, the standard deviation is less than the standard deviation of the population. What that tells you is the distribution of sample means has the same center, but it's not as spread out as far. And then we'll look at some of these examples here on the next page. And the distribution of sample means become less and less spread out as the sample size increases. So here are the possibilities we have. So with any population distribution, you'll see that we have a mean listed, we have a standard deviation, and the population can be any kind of distribution. If the sample means that you're pulling, or if you're pulling samples of size 30 or greater, the distribution of the sample means will always be normally distributed. And you can see that here in the picture, that it didn't matter what the population distribution was, this is normally distributed, as long as your sample is size 30 or greater. If you start with a normal population distribution, so you start off with a normal distribution, then obviously the distribution of the sample means will also be normally distributed. Okay, but what you will notice is that we have the same mean here, but you'll notice on the population distribution, these are spread out more than they are on the distribution of sample means. And that's what all of this up here was telling you. This is just putting it into a graphic so you can see it a little bit better. All right, so what we're going to now do is we're going to interpret the central limit theorem for a couple of problems. So on the first one, it says that we have a study analyzed the sleep habits of college students. Study found that the mean sleep time was 6.8 hours. So if you come in here to about 6.8, that's where your mean is. That's 6.8. And we have a standard deviation of 1.4 hours. So if you go out 1.4 hours, so if you go down 1.4 hours, that would be 5.4. If you go up 1.4 hours, that would be like 8.2. So this is the how they're spread out. Don't have them over quite far enough, but that's the standard deviation of 1.4 hours. Okay, what we're going to do is take random samples of 100 sleep times from the population. And the mean is going to be determined for each sample. They want us to find the mean and standard deviation of the sampling distribution of means. So obviously we can't do this the long method that we did on example 1 because we don't have all the individual numbers. So we're going to have to rely on the central limit theorem. So the central limit theorem tells me that the mean of the sample means is equal to the population mean. So they told me that the population mean was 6.8 hours. So the mean of the sample means will be 6.8 hours. So that's how easy that is to find. You just have to use the central limit theorem to understand that those are equal. And then we're going to find the standard deviation. So we're told from the central limit theorem that the standard deviation is the standard deviation of the population divided by the square root of the sample size. So when we do that, we're going to do standard deviation of the sample means is equal to the standard deviation of the population divided by the square root of the sample size. So the standard deviation of the population was 1.4 divided by the square root of, and our sample size was 100. So 1.4 divided by square root of 100, which comes out to 0.14. And that would be the standard deviation of the sample means. So you can see how the central limit theorem creates a problem that we can do that quickly, as opposed to all of this work we did up here on step 1. And remember, I didn't even write it all out. I just kind of got you going on the right track to remind you how we did it back in chapter 2. So instead of having to do all of these steps that you're looking at in example 1, we're able to find those numbers immediately if we know those numbers for the population. Okay, and then you'll look down here, and this just show. I put this graphic in just for you to see that when you do that, the sampling distribution of the sample means, and you create that graphic, you can see they are normally distributed, but you can also see that everything's very close together here. It's very narrow. And that was one of the things that it talked about. The distribution becomes less and less spread out as the sample size increases. So if I have a sample size of 100, that's why these values are not very spread out very much. They become less and less spread out. All right, example 3. This time we have the training heart rates of 20-year-old athletes. They're normally distributed. That's important because if they're normally distributed, it doesn't matter what sample size we use. Again, and I keep going back and forth, but I want you to keep this in your mind, that if it's a population from any population and it's not normally distributed, we have to have sample size of 30 or greater. But if the population is normally distributed, the sampling size doesn't matter. So we can use any sample size. And so that's what they're telling us here, is that because we have a normally distributed population, the sample size can be anything. So we're looking again for the mean and standard deviation of the sampling distribution of sample means. So once again, the mean of the sample means is equal to the mean of the population, and they told us that the mean was 135 beats per minute. And that's all you have to do on that one. On the standard deviation of the sample means is equal to the standard deviation of the population divided by the square root of the sample size. So they told me the standard deviation of the sample was 18, and we were doing samples of size 4, so divide by square root of 4. So 18 divided by square root of 4 is 2, and that would equal 9. So the mean here was 135 beats per minute. Just to put it back into the context of the problem. And the standard deviation of the sample means would be 9 beats per minute. And remember, that's also called the standard error. So we've got a mean of 135, a standard deviation of 9. And then what you can see here, because we had a smaller sample size, you will notice that the population was normally distributed with a mean of 135. Standard deviation was 18. So if we went down 18 or up 18, that would be our standard deviation. When we go to the distribution of sample means, we have the same mean, but now our standard deviation is only 9. So the standard deviation, we're not spread out as much. You will also, to compare this one to the previous example, we said that when we have a greater sample size, the numbers are less and less spread out, which is one of the things right here. The distribution of the sample becomes less and less spread out as sample size increases. So this one had a large sample size, so everything's really close together. This had a smaller sample size, so it is spread out more. Okay, part 3, we're going to be looking at probability and the central limit theorem. So we're going to bring in some familiar terms from previous sections, and then also the standard error that we've talked about in this section. So in section 5.2, we learned how to find the probability that a random variable x will lie in a given interval of population values. And so similarly, we can find the probability that a sample mean will lie in a given interval of the sample mean sampling distribution. Okay, so we're going to go back and we're going to be finding z-scores again, like we did back earlier in chapter 5. To transform x bar, which remember is the mean of a sample, to a z-score, we're going to be using this formula. So it's going to be the value that they give you minus the mean divided by the standard error, which is, we've been using standard error on the previous examples. All right, so let's put this into an example. It's a whole lot easier to explain with actual numbers. So what we have is a figure that's showing the average miles driven each day by age group. So you're going to randomly select 50 drivers ages 16 to 19. And this is the whole population. We're told that the age group 16 to 19 drive an average of 20.7 miles a day. The age group 20 to 29 drives an average of 31 miles per day, and so forth. So this chart over here with the cars in it, that's giving us all the numbers that we're going to need. All right, so it says you randomly select 50 drivers. Okay, that is important because they did not tell us that anything is normally distributed. So if it's not normally distributed, your sample size has to be at least 30. So we have a sample size of 50. So we have n equals 50. It's important to recognize what they're telling you. You randomly select 50 drivers ages 16 to 19. So we're doing n equals 50. And then we want to find the probability that the mean distance traveled each day is between 19.4 and 22.5 miles. And we're assuming a standard deviation of 6.5 for the population. So what we're going to do is, since the sample size is greater than 30, that means we can use the simple limit theorem. And we're going to conclude that the distribution of sample means is approximately normal with a mean and standard deviation equal to the numbers we can calculate from the population. So we know that the mean of the sample means is equal to the mean of the population. So what you're going to do is you're going to calculate the mean of the population. So what I'm doing is finding the mean of the population. And I'm going to get that by calculating. I didn't write all these numbers down, so I'm having to do them on my calculator right quick. You're randomly selecting 50 drivers ages 16 to 19. And so all we're looking at on this particular table is the 20.7 miles that the 16 to 19-year-olds drive on average. So when we're looking at this, because we're selecting 50 drivers from the 16 to 19 age group, we're finding the mean of the population mean, then this is the mean or the average number of miles driven by that population of 16 to 19-year-olds. So when we select the sample of 50 drivers, it's also going to have an average of 20.7 miles. So they give us all this information, but notice they're just asking us about the 16 to 19-year-olds, so I'm only looking at that first box there. So that would be what is the problem? That is the mean of the 16 to 19-year-olds. Okay, when we go to standard deviation, and the reason I'm calculating these is because the formula will ask me to find the value, the mean, and the standard error, so I'm just calculating them ahead of time. So then for my standard deviation of the sample means, it's going to equal the standard deviation of the population divided by the square root of the sample size. So when I calculate this, I'm going to get the standard deviation of the population, and and I'm not going to work all of these out here, is given to me as 6.5. And then the square root of n's the number of people in our sample, which was 50, divided by the square root of 50. And like I said, I'm not going to put the individual numbers here. You can put all this in your calculator at once. 6.5 divided by the square root of 50 is approximately 0.9. Okay, so these numbers we're now going to use when we come up here and do our z-score and find our probability. So what is the probability that the mean distance traveled each day is between 19.4 and 22.5? So we're using the 19.4 as one of my values, and we're going to use 22.5 as my other value, and then we're using the mean and standard deviation that we just wrote down. So I'm going to write down the formula. It's always a good idea to write the formula down. Every time you use it, it helps you to ensure you're using the right formula and putting the right numbers in. So I'm using this formula, which is the x bar minus mu of x bar, which is the mean minus the mean of the sample means, divided by the standard deviation, or the standard error. And then this is going to be, for the first number was 19.4, minus my sample that I just, or my sample mean that I put up here, 20.7, divided by, and then my standard error that I just found, which was approximately 0.9. But what you're going to notice here is it's going to be necessary, and because I've noticed some people missing these on test, because we round too soon in the problem. If I use 0.9 here in this problem that I'm about to do, if I use just 0.9, it's going to throw my answer off. So what you need to make sure you do here is either put in the 6.5 over square root of 50 down here, or to make it a little bit easier on you, if I do 6.5 divided by square root of 50, even though my answer I rounded to 0.9, I need to actually keep a bunch of decimal places. So I'm going to put 0.91923. So instead of just putting 0.9 here, we're going to keep about 5 or 6 decimal places. And I've mentioned that in previous lessons that you don't want to use rounded numbers in the beginning of your problem, because then it makes your final answer off. And that's why some of you are missing your questions on your test by like 1 decimal place. It's because you're rounding too early in the problem. So once I do this, I'm going to do 19.4 minus 20.7 and get negative 1.3. And then I'm going to divide by that 0.91923. And if you keep 5 decimal places, you should be good. Shouldn't be a problem with rounding too early and getting the wrong answer. And this comes out to approximately negative 1 point. And on these, I think the typical problems are going to ask you 2 decimal places on your z-scores. So negative 1.414, which would be negative 1.41. So that's my first z-score. Okay, and then my second value they gave me was 22.5. So I'm going to go through the same process again, but this time using the 22.5. So I'm going to do 22.5 minus the mean of the sample means, which was 20.7, divided by the standard error, which is that 0.91923 number. So when I do this, I get 1.8 over this number. And that one comes out to approximately 1.96. So what I've done is I've created z-scores, and now we're going to tie these back in with what we were doing in the previous sections in Chapter 5. So I want the probability that my value falls between 19.4, or my sample mean, or x bar, falls between 19.4 and 22.5, is going to be equal to the probability that the z-score falls between negative 1.41 and 1.96. And then these are the ones where we use our tables to find our answers. So I don't think I didn't include the tables here, but remember these go back to those tables that I've included in the previous examples. And I told you where you could go in and print those off, so you would just have them there to use every time. So when I do this, this would be the probability that Z is less than 1.96 minus the probability that Z is less than negative 1.41. And again, this comes from a previous lesson in chapter 5, so I'm not going into detail how to do this because we just got through doing it in one of the previous lessons. So these will come from, again, from our standard normal table that we looked at, and the probability that Z is less than 1.96 is approximately 0.9750 minus, and the probability that it's less than negative 1.41 is 0.0793. And when you subtract those two, you end up with 0.8957. And that would be our probability. Okay, so the interpretation of this, and this is showing you from the table, from the graphic. I didn't include the table, but I did include the graphic here that we're looking to find between, if we want the average driving distance between 19.4 and 22.5, when we create the z-scores from that, we're looking for the z-score to be between negative 1.41 and 1.96. Remember, when we calculate these or we look at the tables, they give us, when I look up 1.96, it's giving me everything below 1.96 all the way down. So that's why I have to subtract off the values that are less than negative 1.41 so that I get what's in the middle. And again, that was explained in a previous section. Okay, the interpretation here, putting this back into words, because a lot of times that's what you have to do on the test, is once you find your answer, you have to describe what you found. So the answer in this is, of all samples of 50 drivers, and again, we were focusing just on the ages 16 to 19, we ended up with 0.8957, so that's about 90%. About 90% will drive an average distance or a mean distance each day between those two numbers that they gave us. So between the 19.4 miles and 22.5 miles. So what you could also say, if we went on the other side of that, instead of the 90%, we could say that about 10% of the drivers drive outside of that. So about 10% of the drivers drive less than 19.4 or more than 22.5. If we've got 90% in here, about 10% fall outside of those numbers. Okay, so that is transferring your values to z-scores and then going back and doing the probability that your z-score falls in those intervals. Okay, a couple more examples. Example 5. Finding the probability of sampling distribution again. We have the mean or average room and board at a 4-year college. And we're going to randomly select 9 4-year colleges. What's the probability that the mean room and board is less than 10,750? And again, this is important because we have a sample size of 9 here. It's important that they tell us that the room and board are normally distributed. Otherwise, we would have to have a larger sample of 30 or greater. Okay, so here's what they're telling us. The mean of the population, we're using a sample size of 9, and the standard deviation of the population is 1650. we're going to find the probability that the mean room and board is less than 10,750. So what I have to do is I have to transform that 10,750 into a z-score. So I'm going to use my z-score. And first, though, I'm going to go ahead and do the mean of the sample means and the standard deviation of the sample means, so that I'll have those ready to go. So the mean of the sample means is equal to the mean of the population, which is 10,453. And then the standard deviation of the population means is equal to the standard deviation of the population divided by the square root of the sample size. So 1650 divided by square root of 9, and that comes out to exactly 550. So we'll need those numbers as we go into the z-score. So I'm calculating a z-score, which, remember, is the value that we're talking about in this particular problem minus, and again, if you're looking for I'm finding this, and again, I encourage you to write these down on your formula card. We're doing the value minus the mean over the standard error. So you can remember the symbols. To me, it's a little bit easier to remember the words: value minus mean over standard error. So the value they gave us that we're transforming into a z-score is the 10,750. We're going to subtract from that the mean, which is the 10,453. And we're going to divide that by the standard error, which is the standard deviation of the population sample means, which is 550. So we already have all the numbers we need when we get down here. That's why we found these at the beginning. Okay, so we do this, and this comes out to 297 over 550, which is approximately equal to, or is exactly equal to, 0.54. So what they're asking me is I want to know the probability that the mean room and board is less than 10,750. So the probability that the mean is less than 10,750 will be equal to the probability that the z-score is less than 0.54. And again, you can do these by going to the table, and we look at the table and find the probability for a z-score of less than 0.54, and that would be 0.7054. And so what that's showing me here on the table or in the graphic, we have a mean of 10,500, normal distribution, and we have the value that they were asking me to find was 10,750, and we were finding the probability that randomly selected would be less than that. And that gives me all of this area, which is the 0.7054. So if I want to interpret that, move the decimal twice, that's about 71%. So about 71% of such samples similar to the one in the problem, such samples of n equals 9, or 9 people, or 9 universities in the sample of n equals 9, will have a mean or an average less than the 10,750 that they ask us about. Okay, and then if you look at the other side of that, then about 29% of the randomly selected colleges would have a mean room and board above 10,750. So about 71% has average room and board fees below 10,750, and then about 29% would be above the 10,750. All right, one last thing on number 5 is quick calculator tutorial. And I haven't been creating a separate video showing the calculator because these are real quick keystrokes to get to. So I'm not doing a whole separate tutorial for this. So on the calculator, we are looking for what's called the normal CDF. And the normal CDF is the normal cumulative distribution. So when we do that on your calculator, you're going to push the second button. And again, this is for the TI-84. You're going to push the second button. And then you're going to push the VARS. Oops, I hit the wrong one. The VARS button. And then you're going to see number 2 says normal CDF. I'll write that down below so I have room to write it in. So the second, number 2 says normal CDF. So you're going to push that. And once you push that, it's going to ask you for a lower limit. Mine automatically puts in a lower limit. If it doesn't, then you're going to put in like, for the lower, you want to put a really small number, so like negative 10,000. And then it's going to ask for your upper limit. And your upper limit is going to be the number that we found for this problem, which was, and this is actually, I'm actually going through the steps where we do it from the original numbers, and then I'm going to show you how to do it where we go from the z-score. So from the original numbers, our upper limit was 10,750, and we had a mean of 10,453. So you would put those numbers in. And we have a standard deviation of 550. And we calculate all of that, and it gives me the 0.7054. Okay, so that's using the numbers from the problem without the z-score. If you want to use the z-score, we're going to go through the same steps. Our lower limit, we'll still use the negative 10,000. But now our upper limit's going to be our z-score. So we had a z-score of 0.54. And if we're working off of z-scores, that means we're using a mean of 1 and a mean of 0 and a standard deviation of 1. So you're going to go through those same keystrokes, but you're going to put in your upper limit is 0.54, your mean is 0, and your standard deviation is 1. And when you calculate that, you'll see you get the exact same answer. So this is using the z-score. And then this is using the original numbers without transferring it to a z-score. So there's 2 different things you can do on the TI-84 to help you calculate those probabilities. And these are some of the same keystrokes that we used back earlier in Chapter 5. All right, the very last example for Section 5.4 and for Chapter 5, because after 5.4 we have another test coming up over 4 and 5. So the very last example we have here is we're finding the probabilities for X and X bar. We've got some college students using credit cards to pay for school-related expenses. For this population, the amount paid is normally distributed. That's important that it's normally distributed. And the reason it's important that it's normally distributed is because it doesn't matter what sample size we use, we will end up with being able to use the central limit theorem regardless of the sample size. So I know I've said that several times in this lesson, but it's important that you pay attention to that. The central limit theorem works for normally distributed with any sample size. So we don't have to have that sample size of 30 or greater. So that's important. Okay, they tell me the mean is 1615. They tell me the standard deviation is 550. And question 1 says, what is the probability that a randomly selected college student who uses a credit card to pay for school-related expenses paid less than $1,400? So what we're going to do is we're going to create the z-score, and then we're going to use the table to find the probability of that z-score. So the first thing I want to do is we're looking at a person using, or the number that we're looking at is 1400, and we're using the mean as 1615, and we're using the standard deviation as 550. So on part 1, my z-score is going to be x minus mu over standard deviation. So 1400 minus 1615 over 550. That comes out to negative 215 over 550, which comes out to approximately negative 0.39. So then we're going to go to our probability that the value or the amount spent was less than 1400, would be the same probability as the z-score being less than negative 0.39. And we look that up in our table, and that comes out to 0.3483. So again, you can put these in your calculator to check your answer. Like I showed you on the previous step, you can use the tables that I've told you to print out earlier to find these probabilities. So what we were asked to find is the probability associated with a certain value of the random variable x. And then we found the z-score and then the probability. On part 2, it says you randomly select 25 college students who use credit cards to pay for school-related expenses. What is the probability that their mean amount is less than 1400? So in the first one, we just randomly selected a college student. So we weren't doing the sample of the sample means or the mean of the sample means. We were just doing a single college student. Well, now we're randomly selecting 25 college students. So now we're asked to find the probability associated with a sample mean. So since we're finding the probability of a sample mean, then we're having to go to our other z-score formula, which is x bar minus, and then this is the mean of the sample means, over the standard deviation of the sample means. So we'll come up here, and we're still using the 1400. And remember, the mean of the sample means is equal to the mean of the population. So 1615 stays the same. But down here, we have, remember I'm going to come back and put it in over here now that we've got that written. That's the standard error. So if you remember, the standard error is the standard deviation of the population divided by the square root of the sample size. So it's going to be the 550 divided by our sample size is 25, the square root of 25. So when I do this one, top still comes out to negative 215. These numbers down here come out to 110. So when I divide, I get approximately negative 1.95. So now again, I'm going back to the probability. So the probability that the sample mean is less than 1400 would be equal to the probability that the z-score is less than negative 1.95. We find that either using the technology, the calculator, or using the table, and this would be 0.0256. All right, and then you can tell that, and if you're using a calculator, I'm just going to point this out. If you're using the calculator, your answer may vary slightly from the answer in the tables that's located in the appendix of the book, and that's just because of rounding. So your answers will vary just a little bit sometimes when you're using technology instead of the table, but it's not going to be enough to make your answer wrong. Okay, and then part 3 just says to compare or interpret what we found in parts 1 and 2. So our interpretation is there is in the first one, 30.348, so that'd be about 35%. There is about a 35% chance that a college student And of course, these are college students. In the problem, it says college students who use credit cards to pay for school-related expenses. So based on that, there's about a 35% chance that a college student who uses a credit card will pay less than $1,400. But then if you go to the mean amount of a sample of 25 students, so if you randomly selected 25 students, the probability that those students would be less than 1,400 is very small. It's only about 3%. So if you move the decimal twice, 2.5 or about 3%. So on this one, there is only about a 3% chance that the mean amount a sample of 25 students will pay less than 1,400. So if you choose just one student at random, there's a 35% chance that that student's going to pay less than 1,400. But if you take a sample of 25 students, there's only about a 3% chance that the mean amount the sample spends will be less than 1,400. And then if you go back to early on, we talked about what's considered unusual, and we said anything below 5% would be considered unusual. So definitely the part 2 part would be considered unusual if they ask you that. So it would be unusual that those students would pay less than 14%. Okay, the next thing you'll have after this lesson will be, I will be putting up your review to get ready for exam number 3, and that will cover chapters 4 and 5. So you'll be looking at sections 4.1, 4.2, and then 5.1, 2, 3, and 4.